To section 4.3, which is logarithmic functions. This is a widely misunderstood section, I think. So far, I think the vast majority of everything we've done has been familiar and hopefully not too difficult. But I find in my experience that logarithms, for some reason, people don't do well with logarithms. I don't know why it is. I don't know. Maybe a lot of people skip them in previous math classes in high school. I don't know what your experience is with logarithms, but they really shouldn't be that bad. So let's begin our thinking of what logarithms are. And to do that, I want to do it through thinking about roots to begin with. So let's just take a little side detour and think about what roots are when we define them, right? I'm confident that all of us were just puzzled when we were first given that little notation. What in the world is that little house, and what does that do, right? So by default, we start off with 2, so there's like an invisible 2 there. And so we have to memorize these, right? What's the square root of 4? Okay, well, I don't know about your house, but in my house, we sat in the kitchen and my mother would hit me with a ruler every time I got it wrong. That's how you learn math. So you just have to memorize it. Square root of 4, okay, it's 2, right? Square root of 9, okay, it's 3, right? You're just memorizing it. And the square root of 16, oh, okay, it's 4. Where does that come from? Well, it's coming from your multiplication tables, right? You have to know your multiplication tables in order to know these answers. So we know that the answer here is 2 because 2 squared is a 4, right? And we know that the answer here is 3 because 3 squared is 9, right? And we know that the answer here is 4 because 4 squared is 16. So this is really just a way of checking that you know your multiplication tables, right? It's just the multiplication tables in reverse. But if you don't know your multiplication tables, then you won't know the answer, right? So if, for example, okay, like, let's get really clever here. What's the square root of 529? I don't know. I have no idea, right? There's no way to know that without technology unless you know your multiplication tables. There's nothing we can do to the 529 to get the answer, right? Just like over here, when we were trying to figure out the answer to 16, we didn't really do anything to the 16. We didn't add, divide, multiply, all those common operations we're used to. There were none of them there's no operation we can apply to this, and none of those common typical operations to get the answer. So if you don't know your multiplication table, there's just no way to know what this is, right? So you can't know the roots. You can't find the answer unless you know your multiplication tables. Now, if you happen to know your multiplication tables, or you have technology, then you can find the answer. And this is, the answer is going to be 23, and that's because 23 squared is equal to 529. But you can't know that unless you know your multiplication table or you have technology. Okay, now by default, there's a little 2 that goes in here. 2 squared, 2 squared, 2 squared, 2 squared, right? And then that lets you know that we're talking about squaring all your numbers. But if we were talking about something different, what if we had the cube root? Cube root of 8. The cube root of 8 is equal to 2 again, and that's because 2 to the 3rd power equals to 8. But just like before, you wouldn't have known that answer unless you know your multiplication tables, unless you know that 2 times 2 times 2 equals to 8, right? That's the only way. If you didn't know that, if I just gave this to a 3rd grader and they don't know this is true, there's no way to find the answer for them, right? That you can't take 8 and divide it by 3. That's not going to give you the answer. You're trying to figure out blank times blank times blank equals to 8. What is that blank? Well, that's hard to know unless you know this multiplication table, right? Okay, and then over here, if you want to find the cube root of 27, right? The answer is 3. Because, again, because 3 to the power of 3 equals to 27, okay, and so on and so forth. Okay, so cube roots and raising things to a particular power are associated, and we want to do the same sort of connection one more time. So we've been looking at exponential functions, and whenever you when you do multiplication and you want to find its reverse, kind of undo the multiplication, you go to roots, right? So multiplication, 3 times 3, 4 times 4, right? Multiplication, and roots are inverse operations, right? They kind of undo each other. Okay, so now we've been working with exponential functions, So we've had something like, let's say we had f of x equals to, let's go with 2 to the x power. And we created a table of values. We've worked with this before, where we have x and we have 2 to the x power. So when we have 0, that leads us to 1. When we have 1, that leads us to 2. When we have 2, that leads us to, oops. When we have 2, that leads us to 4. Okay. That leads us to 4. When we have 3, that leads us to 8. Right? 2 to the third power is 8. Negative 1, that leads us to 2 to the negative 1 power, which is going to be 1/2. Negative 2, that's going to be 2 to the negative 2 power, which leads us to 1/4, right? And so on and so forth. These are exponential functions, right? An exponential base 2. So we want to be able to go backwards, right? In reverse. What is the value of x such that 2 to the x power gives us this particular output? And that's where we defined logarithms to come in. Right? So in order to go backwards, just like roots undo multiplication, logs undo exponential. So we're going to come up with this notation. Log, oh, that looks ugly. Log of x, log of the input. And again, we're going to put this little base here so that people know what we're talking about. And so what happens is that we're going to be able to go backwards. Log base 2 of 8, right? This is this number right here. And so the output of that function will be this one. The answer will be 3. Log base 2 of 8 equals 3. And this is just like before, because 2 to the power of 3 equals to 8. Just like when roots, right? What's the square root of 529? I have no idea. I have to know my multiplication tables to be able to get this answer. Otherwise, it's just a weird notation that I don't know how to solve. There's nothing I can do to the 529 to get the answer. I can't divide it, add it, subtract it. This little base 2 doesn't help me at all. There's just no real way of finding an answer unless you know your multiplication tables. And same thing with this. When I look at log base 2 of 8, let me copy that again, log base 2 of 8, there's no way for me to know the answer without knowing this table. I can't do anything to the 8. This 2 doesn't help me. I don't know how to fix it from here, right? I have to know this table over here. So really, this log is just something that's letting you know to go to this table and read it in reverse. And that's all you can do. There's no fancy math here. The only way I know that the answer is 3 is because I've memorized this. Just like up here. The only way I know that the square root of 16 is 4 is because I memorized it. Right? It's been memorized. And logically, it comes from knowing your multiplication tables, and I know that 4 times 4 is 16, and that's why I know it's a 4. But it's not an operational symbol. It's not an operation I can do to the 16 to get me my answer. Okay? So let's do a couple more then. Okay, so let's say forget the 8. Okay, how about log base 2 of 1/4? Right, what can I do, right? So this is saying 2 to what power equals to 1/4, right? So the answer to this, whatever this is, will satisfy the statement 2 to what power equals to 1/4. Right, and as I keep harping, there's no way to know that answer unless you know this table here and you understand it really well, right? I don't know, maybe the word log, the fact that we have this log thing is really intimidating. You know, as you read this, people get stuck here, their eyeballs go here, and they think, log, what does carpentry have to do with math? I don't know, I don't understand that. Does this stand for something? Is this an acronym? The L stands for something, the O stands for something, the G, you know, people just get stuck with this word here, but it's just a notation, just a symbol that's asking us to read this table in reverse, right? I like to think of it as, you know, maybe ancient Greek or something, or Latin. It's ancient Latin for go to this table and read it in reverse. That's all that means. Just like the first time you saw this little root notation, you know, like, what the heck does that mean? Why are we drawing like this weird little symbol? What does that symbol mean? You know, you probably got stuck on it for a while until it became really comfortable, really familiar, and then it didn't scare you anymore. Well, this log thing seems to scare people a lot. But you shouldn't focus there. Whenever you see a log, your eyeballs should jump right into this right here. It means to read an exponential function of this base in reverse, right? So don't get stuck with this word log. Run over here and read this, right? In general, if we have a log function, log base 2 of some value x, let's say just a and b, of some value a, then the answer is b, and that's going to be given that this means, right, because look at the pattern. It's this raised to that power equals to this. So there's this little cycle that happens here. This raised to that power equals to this, right? So it'll be 2 to the power of b, if and only if. I should have said, not because, I should have said if and only if and only if 2 raised to the power of b equals to a. And of course, there's nothing special about the 2. We can also raise it to any power. So if we're thinking about a different exponential function, like f of x, say g of x is 3 to the x power. So again, we can have a table, and we can have x values, and then we can have 3 to the x power values there. 0 still leads to 1, and 1 leads to 3, and 2 leads to 9, and 3 leads to 27, right? 3 to the third power is 27, and 4 leads to 81. 4 leads to 81. Good. And negative 1 leads to 1/3. And negative 2 leads to 1/9. Good. So now if we have this, what is log base 3 of 27? This is the same thing as asking you 3 to what value equals 27? Good. That's what this is asking you. 3 to what value equals to 27? And again, the only way to know that is to know this table really well. So I'm just reading this in reverse. They're inverse operations. 27 is right here, therefore the answer is 3, because 3 to the third power is 27. Good. And I can say, what is log base 3 of 1/3? Oh, the answer is -1, because 3 to the -1 power equals to 1/3. Note that, okay, so if we have log base 3 of 81, well, that's going to be 4. 3 to the 4th power equals to 81. However, log base 9 of 81 is 2. Right? 9 to the 2nd power is 81.
Okay, now I'm going to continue the exact same concept using Excel, because this is a really important people often get wrong. But if you feel like you kind of get it already, then please feel free to jump ahead.
All right, good enough. Okay, so here are tables, including all our powers, right? So I put power here because I knew that the Excel program was going to put x, it's going to do this. If I had done it, I would have done that, and I know we're not used to doing that. So we could still write this down as like function notation. If this is the input x, then, oh, that's so thick, okay, then this would just be x squared. We can also write it down as f of x equals to x squared, right? So we're squaring all our powers, 0 squared, 1 squared, 2 squared, right? The input is this guy, and the result is that we squared, and here's our table. Raising to the power of 3, here's our input x, and so here's some other function, I don't know, I can use g of x equals to the input raised to the power of 3, right? The input gets cubed, and here's our little table, right? 4 times 4 times 4 is 64, and 5 times 5 times 5 is 125, right? That's what these values are. Let's just confirm some of these things. So this one right here is 3 times 3 times 3. That's what 27 is, right? And this one is 6 times 6 times 6, right? Okay. Then we have this other case over here. This is an x, and then this one is some other function. Let's call it h of x equal to x to the power of 5. Right, so 0 times 0 times 0 times 0, 5 different times. That's how we get this. 1 to the 5th power, that's still 1. 2 to the 5th power, that's 32. 3 to the 5th power, that's 243, right? So this guy right here, for instance, is 3 times 3 times 3 times 3 times 3. 1, 2, 3, 4, 5 different times. That's how we get this 243. And then self-explanatory for these, right? So let's just write down a function for it. I don't know, about x to the 8th power. Good. Okay, so we have all our tables, and we learn these, and then we want to learn how to go backwards, right? To go backwards on these tables where you have an input raised to a constant power, that's when we invented roots, right? So roots, so if we go root 3, right, the index of the root is this little 3 here, it means to go to this table, right? As soon as you see this index, this notation, this symbol, it means go to this table and read it in reverse, right? You're going to go to this table and read it backwards. That's all you're doing. There's really no magical new power you learn from this. It's just learn how to use the table and go backwards, or have it memorized, right? So if we see the cube root of 729, you either have this whole table memorized, or you're brilliant, or you have a calculator, or you have a table. And you go to the table and you see, okay, well, it's cube 3, root 3, so we got to go to this one. And then we got to read it in reverse. And so that's how I know that my answer is 9. Good. Or if we see another table, and okay, this one says root 10 of, wait a minute. All right, the 10th root of 59,049. Okay, so I know that I have to go to this table over here, something raised to the power of 10. And then I have to look for this number, if I can find it on my table. And that's how I know that the answer is 3. Right? There's no magical property to this root notation. You just have to know to look at the table. Now this works for the whole number values. Of course, what about decimal values? Okay, well, we have to extrapolate from that a slightly different idea, or thinking about the graphs and thinking about approximations. But in terms of whole number solutions, this little notation here should not be that special, right? We should at least get a concept of what this means, right? We have to go to this table. We have to read it in reverse. That's what this means. Good? Okay, so raising an input to a constant exponent is related to roots, right? Okay, so we're going to do the same thing with exponential powers, but we want to go backwards on those. So let's do that with this thing again. So I'm going to change this to say base 2. Okay, well, that was a long investment. Hopefully it pays off for anybody that's still a little bit confused. Okay, so then we have new functions. Now we have a slightly different situation. In the previous one, we had x squared, and here we have exponential functions. So this one, for example, could be written as 2 to the power of x. So this one could be f of x equals to 2 to the power of x. So as a result, say this one, this 8 right here, is the result of 2 to the power of 3, which equals to 2 times 2 times 2. So how we get that. And say this one over here is 2 to the power of negative 3, which is the same thing as 1 over 2 to the power of positive 3, which is the same thing as 1 over 2 times 2 times 2, equals 1 over 8. 1/8 gives you 0.125. Good. Okay, so then these ones, let's scoot this down a little. So let's move on to these. So if I define this as some function h of x equals to 3 to the x power, we get this one, and defined in a similar way. This could be some g of x function, which is 5 to the x power, some w of x function, defined as 8 to the x power, and finally some v of x function, defined as 10 to the x power. Okay, so we know how to move forward with these functions. We know that the input is now in the exponent. That's different from before, right? That's similar to the previous one where we had x to the second power. Don't confuse these two, right? The input is the base being squared for the previous functions, whereas here we have the whole number, the constant value of 2 is the base, and the input value is the exponent. Okay, so they're a little bit different. And now if we want to go backwards, with these, to go backwards, the reverse was, the inverse of this was roots. Inverse. Oh man, this is not helping. I don't know why sometimes my computer is doing great and sometimes it just really does not like life. Okay, the inverse is roots. Okay, well, in this case, the inverse, to go backwards, to read this table in reverse, we're going to use the notation of logs, right? That's where logs were created. So when you see the word log, there will be a little index here, just like in roots. So let's say, for example, we see log index 3 of something. And all this means, this word log, means to go to this table. The table that involves exponential functions base 3. Go to this table and read it in reverse. That's all this means. Log base 3 means to go to this table, and whatever's in here, like maybe there's an 81. Okay, well, here it is. I got to go backwards. The answer is 4 because I looked it up in my table, right? So you either have these things memorized, or you have a table in front of you, or you have technology in front of you. That's really it. There's no other way to really get the answer to this unless you have a table or you have it memorized. Good. We see log index, and the index of the log is log index 5. We know to look at this table, right? And so now, in order to get this answer, say if I see a 125 in here, 125, then I know that, okay, I got to go to this table, it's index 5, so I got to take this table and read it in reverse, and that's how I know that the answer is 3. Good. Any questions at all? Kind of? Maybe? Sort of? I don't know if it's demystifying logs. Log index. So notice that some of these numbers are the same. I didn't put any of those in here, did I? So for example, note that log base 8 of 64, that needs to go to this table. Oh, here's 64, read it backwards, so that must be a 2. Right? And for the same reason that it's just reading this table in reverse, then we can also take each one of these statements and say that it must also be true. If this is true, log base 8 is 64, that's reading this backwards, the answer is 2. It must also mean that 8 squared equals 64. Right? So there's this little circle of life that happens here. Start by looking at the index of the log, and then you go over here, raise it to that power, and it must be equal to this. Right? Just like over here, this raised to that power must be equal to this. This raised to this power must be equal to that. Right? So 3 to the 4th power must be 81, and 5 raised to the 3rd power must be 125. Okay, so exponential functions in general, as we remember, will have this sort of a blue shape, this graph right here in blue. That general shape, as long as the base value is bigger than 1, right? Remember, bigger than 1, it has this shape. As long if it's a value between 0 and 1, it'll flip in the other direction and come back down this way. But for values that are bigger than 1, it has this sort of a shape. It always goes through the point 0, 1, right? And notice that all exponential functions are 1 to 1. Right? If we apply that horizontal line test and move around a vertical bar, that's what these red lines are. So imagine us being able to sweep this red line up and down, up and down, up and down, and keeping track of how often it crosses the blue curvature. It will always touch at exactly 1 point. It never touches at 2 points. So therefore, it's 1 to 1. Remember, 1 to 1 means that for every unique input, there's only one unique output, and that for every output, there is one unique input that led to that output. That's what it means for it to be 1 to 1. So that way we can go forwards and backwards on this. If I told you, what is the input value that led to the value B? Well, there's only one, this one. Good? Yes, 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 yes. Okay, so because it's 1 to 1, we know that there exists the possibility of having an inverse function. So the inverse function, f inverse, is called the logarithmic function. Right? So the logarithmic function is, with base a, denoted by log base a, is the inverse function of the exponential function of an exponential function base a. Right? So that's where this is coming from. So we started working with this. We know an exponential function is this. And remember, x and y are just dummy variables. But what's important here is that they undo each other. They go forwards and backwards, right? So we started life working with exponential functions. So if we had a to the power of something in here, which is the input of an exponential function, input, usually x, but it's just a dummy variable, it doesn't matter. The input goes there, right? And then we have the base a, which is a constant, and then that led us to some output, right? Okay, but now if we want to undo this process, reverse it, get back to where we started, then that's where this logarithm situation comes from. We're going to have this new function that would denote by log base a. And now this output of the exponential, this guy, is the one that goes in there. And the output to this log function is going to be what we started with. This guy. This guy is going to be there. So it's sort of a round trip. If we started out with, just to arbitrarily pick a number, if I started out with 5 goes in there, it's going to give me some number here, some number. And we take that some number and we plug it in here. And then the output is going to be 5 again. They undo each other. Good, good, good. Questions, questions, questions? No, no, no? Okay, so then let's see if it helps to go back and put variables on there. And again, we use x and y way too much, so let's just pick some random number, some random letter. Let's say w is the input there. A to the w power equals to, I don't know, how about n? I don't know, how about n? Whatever. So x and y are arbitrary. We use them way too much, whatever. Let's say that in an exponential, these are exponentials over here. Exponentials. And then these are logarithms. So in exponential land, we have this. Here's our input, the W letter, right? Is the inputs. And our outputs are n values. But now we come over here and we apply that value, log base a, and we apply the n in here. That becomes the new input into here. Then the output is going to be that W. Good. And that's what this is expressing. Log base a of x equals y, input gives you this output, if and only if it's true that this base raised to this power equals this. Good. So again, to this idea that there's a sort of a cycle of life that happens here. This is true if and only if this base raised to that exponent is equal to the value right in there. Right? A to the y power equals to x. Any questions so far? Good. So let a be any positive number where a is not 1. It's the only thing we're ignoring. Logarithmic function with base a denoted by log base a is defined to be this. Log base a of x equals to y if and only if it's true that a to the y power equals to x. So log base a of x is the exponent to which the base a must be raised to give x. Okay, so we can go back and forth between these two things. They give you two equivalent statements. A to the power of y equals to x is the same thing as log base a of x equals y. Okay, so let's look at some more examples. Going back and forth between logarithmic form and exponential form, so you can always go back and forth between the two. So log base 10 of 100,000 equals 5, if and only if it's true that 10 to the power of 5 equals to 10,000. Good. And we already looked at log base 2 of 8 equals 3, if and only if it's true that 2 to the third power equals to 8. Right, so whenever you see these and you want to go into from logarithmic to exponential, remember that it's this little circle here. This base to that power equals that number. Right? This base to that power equals that number. Right? That's what this is. So in general, this base to that power must be equal to that number. This is what this is. Good. It's important to understand log base a of x is an exponent. So for example, the numbers in the right-hand column of the table in the margins are the logarithms base 10. So 10 is a very popular number to use, as I mentioned a minute ago. We work with a base 10 number system, therefore some nice things happen when we work with base 10. So look at how nice this property is. If x is 1, then log base 10, and so this guy right here, this guy is saying that if we have log base 10, and we input a 1, the answer is 0. And why is that? Well, 10 to what power equals to 1? That's what this is really asking you. 10 to what power equals to 1? And as we know, any number raised to the power of 0 must be a 1. That's why this is a 0. That's why we get an answer of 0 there. Good. And then let's say this guy right here. This is 10 squared, so log base 10 of 10 squared. Right? And we know 10 squared is the same thing as 100, equals to what? Right, so that's the same thing as asking you log base 10 of 100 equals to what? Right? These both are saying the same thing. And so if we know our powers of 10, 10 to what power equals 100? Well, obviously 2. And, well, it was already given in this form, so that makes it nice and convenient. We start to see a pattern that when the input is given in powers of the base, it matches with this base, then it's really just the exponent that equals our answer. Does that make sense? It's kind of like when we're doing square roots, square root of 9, like I don't know how to do that. But if they gave you square root of 3 squared, you're like, oh, obviously the answer is 3 because they're giving you the 9 in the form of something squared. So the square root of something squared is just going to be that number, right? So here it becomes obvious that the answer should be the 3. Well, same thing here. They're presenting you the input in terms of this base raised to an exponent. So obviously the answer is going to be that exponent. 10 to what number equals this? Remember our little cycle. This base raised to that exponent must be whatever's in there. 10 to what exponent equals to 10 squared? Well, obviously the exponent must be a 2. Right? That's why this little pattern begins to form, and things work out really nicely with base 10. So it's a very popular base to use in math, just because things work out really nicely. Some nice properties. Okay, so let's look at some of these. Again, the answer is given, but let's fill out the because. Right, our little cycle of life here. Log base 10 of 1,000 equals to 3 because 10 to the power of 3 equals 1,000. 10 to the power of 3 equals 1,000. Right? And log base 2 of 32 equals to 5 because 2 to the power of 5 equals 32. 2 to the power of 5 equals 32. Right? And the only reason I know that is because I know my powers of 2. I've had that memorized, and that's why I know that. If you don't have your powers of 2 memorized, you won't know it. Luckily for us, you don't have to have a lot of these memorized because we do have technology. So you could just type in log base 2 of 32 and just get your answer, and that's fine. But it's important to understand why the answer is 5, right? So even if you don't know your powers of 2 to a really high number, at least you can understand why the answer is what it is. Good. So then 10 to the power of negative 1, 10 to the power of negative 1 equals to 0.1. Right? That's why this is true. And finally, the answer, log base 16, log of 4 base 16, log base 16 of 4 equals to a half, if and only if it's true, that 16 to the 1/2 power equals to 4, right, which is true. When we apply the inverse function property of our functions, we get this, log base a of a to the x equals to x, and a to the log base a of x equals to x. Right? They undo each other, so they sort of represent a round trip into these functions. Right? So if y equals to a of x, a to the power of x, right? We start with this input here, and we get this output. Okay, so the output is a to the x, and now we apply that whole output to log base a. Here's log base a of, and we input this y right in there, right? So we take that y and we put it right in there. Well, that y is a to the x, log base a of a to the x, because that's what y is. And then these two things will undo each other. A to what power equals to a to the x? That sounds like a simple riddle that's confusing, right? A to what power equals to a to the x? Well, this is just going to be an x. Right? That's what this is asking. A to what power equals to the thing that's in here? Well, it's definitely x. Okay, so what did we do? We started with the input of x. We applied it to the exponential function. We get an output. That output gets deposited into the log base a function, and then that undoes whatever this did and ends up giving you the same output. Right? So it's kind of a round trip that happens between these two, and that's what happens with inverse functions. They undo each other. The same thing happens in reverse. If we start off by plugging something into our log function, we'll get some output. We plug that into the exponential function, and they undo each other. And so we undo those two functions undo each other, and we get back to the number we started with. For that reason, there's some nice properties of logs we have to remember. Right? Remember, a log is a function. It's a set of instructions. It's telling you to go look at a table and read it in reverse. It's not a traditional mathematical operation like adding, subtracting, dividing. So therefore, we have to be very careful about what operations we apply, what rules apply to logs. And so they're going to be very clearly outlined, the rules that apply to logs. And only these rules apply to logs. Well, you should only stick to these rules because it's not true that you can just do whatever you want. Distribution doesn't work the same way, and division doesn't work the same way, right? There's a lot of things we can't do. So we have to be careful about what we are allowed to do. And here are a list of some of those properties that are true. Log base a of 1 equals 0, and that's true no matter what, because remember that this little cycle occurs here. This is saying that a to the power of 0 equals to 1, and that's true, no matter what a is, as long as we're looking at a as being a positive number, right? So for all of these, a is strictly greater than 0. A is strictly greater than 0, and a does not equal 1. That's what the value of a is, just like any other exponential number. Okay, so any number raised to the power of 0 is 1. Also, a to the power of 1 equals a. That makes sense. So log base a of a equals 1 is another true statement. A to the power of x equals a to the power of x. So that's another true statement. Good. And then this last one, like I said, is a little bit more confusing. It comes from this property right here, which is why it's it's not as pretty. But let's just try and use one little example to see what it's saying, and we'll see that these two operations undo each other when we get to that. So let's say, for example, we have that log base 3 of 81 equals to 4, right? That's because 3 to the 4th power equals 81. Okay? Because 3 to the 4th power equals 81. So this is a 4. You can say this in place of a 4, right? When my nephew turned 4 years old, I put this on his birthday cake, right? You're turning log base 3 of 81. Congratulations. Blow out your candles. Right? It's the same thing. When you learn to count, you can count 1, 2, 3, log base 3 of 81, 5, 6, 7, right? This is 4. Okay, so you could say 4 times 3 equals to 12, or you could say log base 3 of 81 times 3 equals to 12, right? It's a replacement of it. It equals to 4. Just like square root of 16. You could say 1, 2, 3, square root of 16, 5, 6, 7, 8, right? It's a 4. Okay, so given that it's definitely absolutely a 4, then you could say that 3 to the power of 4 is the same thing as 3 to the power of log base 3 of 81. Right? Because this is 4. We just established log base 3 of 81 is a 4. Okay, well, over here, I clearly know this is 81 by knowing my powers of 3. 3 times 3 times 3 times 3. Whereas here, well, someone that doesn't really know their powers of 3 can notice the pattern that we have an exponential number, base 3, and we have a log being raised to an exponent that is also a log base 3. So these two match, and we have an input of 81. The whole thing just equals to 81, right? Since this is a 4. Good. Think of it this way. The reason it's an 81, right? So log base 3 of 81 equals to 4 because, thinking of our little circle here, because 3 to this power equals to 81. So even if you didn't know the actual number, it would still match. So if I had, the pattern would continue. So if I had something like 7 raised to the power of log base 7 of some ugly number, I don't know, 537, something like that. Okay, so I can kind of think about this on the side. What is log base 7 of 537? I don't know. It's equal to some number. Let's leave it as a variable. About, I don't know, it equals to m. And it equals to lowercase q. What does that mean? It means that there is some decimal number out there such that 7 to that decimal number equals to, such that 7 to the decimal number q equals to 537, right? Q is that number. There's some real number out there so that 7 to the power of that decimal equals to 537, right? So this whole thing is that decimal. The decimal such that 7 to the power of this decimal, right? This equals some decimal q, right? And q is the number such that 7 to the power of q equals to that. So now what do you get when you take 7 to that power? Well, it's kind of, no duh, it's exactly the 537. It's a riddle, right? It's like a really obvious riddle that is so obvious that it gets a little confusing, right? This is, by definition, a decimal value, some number, some real number, such that 7 to the power of that decimal equals to 537, right? So get that decimal in your head. And now what do you get when you get 7 raised to that decimal? Well, it's 537. You just told me that this is the decimal that makes this true. Okay, so these two things, as long as they match, this exponent, this base and this little number, this little index to the log, as long as they match, the output is going to be whatever number is in there. Any questions about that? No? I think that's probably the most complicated property that's presented. And so here's some examples of our properties. Log base 5 of 1 equals to 0, and that's why? Because 5 to the 0 power equals to 1. Property number 1. 5 to the 0 power equals to 1. That's why. And log base 5 of 5 to the 8th power, right? Like I can go ahead and figure out what this is. 5 to the 8th power, some huge number. And 5 to the 8th power equals to 5 to the 8th power. So this is kind of an obvious thing. This to this power must be this. So when it's given an exponential form and these two match, well, then the answer is just whatever's in there. Good. And then over here, of course, this one's an easy one. 5 to the 1 power equals to 5. Good. And then this is the one I just mentioned. Log base 5 of 12 in the exponent, 5 to what power? Well, then, of course, we get the same thing. So, for example, let me jump to the answer here. Let me do this. Using my calculator, we'll get to this in a second, but using my calculator, I know that log base 5 of 12 equals to 1.543959 dot, 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 dot. Why is that the answer? Because it must be true that 5 raised to this exponent, 1.543959, must be equal to 12. Right? And we can check with our calculator. 5 raised to the power of 1.543959, rounding, of course. From my calculator, I get approximately 11.999. We can check it. It gives you approximately equal to 12. So log base 5 of 12 is this decimal, right? They equal each other. So when they ask you this question, what is 5 to the power of log base 5 of 12? They're really asking you this. You can also say, what is 5 to the power of 1.543959? Okay, it looks extra confusing here. Like, how are you supposed to know 5 raised to the power of 1.549? What is that equal to? You know, it's kind of hard when you're staring at this. But when you're staring at it in this form, it should make sense, since the answer to this is the decimal such that 5 to the power of that decimal equals to 12. So that's why this answer has to be 12. Okay, so graphs of logarithmic functions. Okay, so we know that if a one-to-one function f has domain A and range B, then its inverse function, f inverse, has domain B and range A, right? They flip-flop, right? All the inputs become outputs, so the outputs become inputs. They undo each other, so their domain and range swap, right? For an exponential function of the form a to the power of x, where A is not 1, and remember, A has to be a positive number, so it's got to be greater than 0, but not 1, has a domain R and the range from 0 to infinity, right? Remember that all of these graphs, all of these functions here, have the two general forms, right? We have either this general shape, it goes like this, or we have another that goes like this. Right? This is all functions that have the form a to the power of x have either this shape or this shape, right? And this shape will happen whenever a is strictly greater than 1, right? So for example, 2 to the x power would look like that, and 3 to the x power will look like that, and 10 to the x power will look like that. The bigger the base, the steeper this climbs toward infinity, and the faster this goes towards 0, right? And it doesn't have to be whole numbers either. It could be decimal values, so it could be 2.7 to the x power. It could be e to the x power, as we've seen, right? So all of these have this sort of shape, and they all go through this point, which is the point 0, 1, because any whole number raised to the power of 0 is going to be 1. Okay, all functions that have this shape are going to be cases where the a is strictly greater than 0, but strictly less than 1. Some decimal number trapped between 0 and 1. For example, 1/2 to the power of x, or 0.37 to the power of x, right? They'll have this sort of a shape. They will still have the point 0, 1. All of them will have that, right? And then, of course, depending on the actual decimal value, they will go a little steeper toward infinity on this end and still go toward 0 on this, right? So for both of these, the domain and range are both the same, though. So for this one, the domain is still all real numbers. Domain is all real numbers, right? We like to denote it like that. And the range is positives, right? From 0 to infinity. Not including 0, so put a little parentheses there, up through infinity. For this one, it's going to be the same thing, right? The outputs are a little bit different. The shape of the graph is different, but the domain and the range stay the same. The domain is all real numbers, and the range is from 0 to infinity. Good? Questions? No? Okay, so if we have a function that's going to reverse all the inputs and outputs, right? It's inverse function, then the inverse function is going to flip these things around. It'll be a new function where the domain is from 0 to infinity, and the range is all real numbers. Right? That's what we're driving at here. The exponential function has a domain of all real numbers and a range of 0 to infinity. We conclude that its inverse function, which is the log base a of x function, is going to have a domain of 0 to infinity and a range of all real numbers. Good. And remember that from our previous study of inverse functions, the graphs of inverse functions have this property. Right? They reflect, they're a mirror image about the line y equals to x. Good. So as we think about the graphs of the log functions, they're going to have two general shapes. Let's put it in green over here. If we think about the line y equals to x, which is this little dotted line here, here's the line y equals to x, then its mirror image about that will be the log function, and its mirror image is going to have a shape that looks like this. Right? These two are mirror images of each other. So this is going to be the function log base a of x, as long as a is bigger than 1. So here's a better graph of that. So this is when we have a is greater than 1. So we have this as a to the x power. They all have this shape. And then its log function has this as long as a is greater than 1. Right, this is the line y equals to x. So the fact that, okay, very rapidly increasing function x implies that log base a of x is very slowly increasing. And so here the a to the x power function grows very quickly. So its inverse function is going to grow very slowly. This approaches 0 as x goes toward infinity. And so this one will approach the y-axis as x approaches 0. Right, so this red line is never going to be equal to the y-axis. It's never going to cross across the y-axis. It's going to get infinitely close as x gets infinitely close to 0. But x could never actually be equal to 0. Good. Here this point exists for this function, 0, 1. Any base number a raised to the power of 0 equals to 1. So its log function is going to have the opposite, right? We're just flip-flopping these, so that it'll be 1, 0. Okay, so sketch the graph of log base 2 of x. Well, we've kind of already done that. We have a nice table for it, and if we just flip-flop all those values, we'll get a nice sketch of it. But as long as we're using technology, let's see what it looks like. All right, so let's pretend we don't know what it looks like. So we begin by creating a graph that has 2 to the power of x. So like negative, there's a 0 gives you 1. There's that dot right there. Let's put it in blue. Okay, so there's 0, 1, and then we can raise, and then 2, 4, and then 3, 8, which is already off grid. But there we go. Right. So this is all the ordered pairs that we get when we get 2 raised to the power of that input. We raise that to 4. That already goes way, way out of screen here. So let's go. That makes it all the way over there. Okay. We can also have some negative values. So negative 1, negative 2, negative 3. Right. And again, we start to see that general shape of a to the x power when a is greater than 1. Good. Okay. So well, we already know that that's what the graph looks like. So let's graph 2 to the power of x. Put it in blue again. So if we kept going, putting in values, we can fill in lots and lots of ordered pairs. Eventually, all those ordered pairs would begin to look like a nice, smooth curvature. So we say that this is the curvature that represents all solutions to 2 to the x power. Okay, so now if I create a new table, and all I'm doing, let's begin by just reversing all of these. I know that the reverse function is just going to have this. Can I just graph a value about I'm just typing this. Just put, yes, it works. Okay, so let's put it in red. Okay, so I know that the original function has the point 0, 1. So I know that reversing these, the inverse function should have 1, 0. If the exponential function 2 to the x power maps 0 over to 1, then its inverse function should map 1 back to 0. Right, so we get that point. Let's try another one. Going backwards, we know that 16 should map back to 4. So we should get this one. Right? So if this function maps the 4 over to the 16, the inverse function that will undo this process, reverse it, inverse functions, should map 16 back to 4. So when we input a 16, we should get a 4. We get that dot. Okay, so we can just go backwards to all of these and create ordered pairs. 2 should map back to 1. 4 should map back to 2. 8 should map to 3. 0.25 should map to -2. 0.125 should map to -3. Okay, and you start to see what the graph should look like, right? Again, we can graph the line y equals to x, and we see that its inverse function is going to be a mirror image reflection about that line. So if we keep going with these red dots, keep going, eventually we'll see that it begins to map out this. So we need y equals, and I need the log function. That's going to be over here. Oh, there it is. Log index 2 of x. Looks like that. Any questions so far? No? So this is 2 to the x power. This is log base 2. Good. Okay, so let's do the same thing where the base is somewhere between 0 and 1. So let's see what this looks like when this is equal to, I don't know, about a half. Get rid of all of this. So we're going to repeat the same process, except this time we're dealing with, let's say, 0.5 to the power of 2. Okay. The power of x. Okay, so when we want to have 1/2 to the power of x, so 1/2 to the power of 0 is still 1. 1/2 to the power of 1, well, that's just 1/2. 1/2 to the power of 2 is 1/2 times 1/2, which is 1/4, which is equal to 0.25. Okay, so that's where we get all these points. And we start to see the general shape of an exponential function that has a base value between 0 and 1. Right? And we can always add a little more. I feel like we need a little more. How about -4? -4 gives you that guy. We can also add some more values this way. How about a +5? How about a +6? How about a +7? Okay, so we start to see the general shape of an exponential function that is 1/2. Let's put 1 divided by 2 power of x. 1/2 to the power of x. And so after a while, we begin to see that shape right there. Good? Questions? No? No. Okay, so now if we start to go backwards on these, we just kind of blindly copying these, and we know that the inverse function should undo this process so that 1 should map to 0. Okay, we already have that one. And let's get rid of these. Okay, so that means that just kind of blindly following these, this function that will reverse this process should map 0.25 and map it over to 2. Okay, we should get these 2 points. Here, the original function mapped 0 to 1, so therefore this function should go from 1 to 0. Good. And then this point over here, we have 0.25, comma 2, and that should be the opposite of this one. No, this one. 2 comma 0.25, 0.25 comma 2. Okay, so kind of blindly going through and copying more of these things. 0.125 and 3 and 0.0625 and 4. We see that as x gets closer and closer to 0, this function seems to be going that way, right? Getting closer and closer to the y-axis. And as we go in this direction, so 2 should map over to -1, and 4 should map over to -2, and 8 should map over to -3, and 16 should map over to -4. You start to get a sense of what this graph will look like. Right? Again, we can graph our line y equals to x, and we see that it should be a mirror image about that line. Good, so let's put 0.5 here. Okay, so I can't do that. Y equals to functions miscellaneous log index 0.5 of x, and let's make it red. There. Okay, so this red line here is log base 1/2 of x, whereas the blue one is 1/2 raised to the power of x. notice that the domain of the blue one, the domain is all real numbers. The output is positive real numbers, right? Anything greater than 0. On the other hand, for the red function, the domain is positive real numbers greater than 0. Those are the only inputs you can put into the red function. And the outputs are going to be all real numbers, right? This goes out toward infinity that way, and this will continue to grow this way, and it never tapers off. It just is growing down toward negative infinity. It's just growing slowly. Questions? No? Maybe? Kind of? Maybe? All right, let's leave this. All right, so we kind of answered that. All right, we can create a table and find some values and graph them, and we get a general sense of the shape of log base 2 of x. And then here are various logs. Log base 2 of x, log base 3 of x, log base 4 of x, log base 10, right? So various shapes of logs. And they are all, again, the mirror image across the line y equals to x to the function 2 to the x, 3 to the x, 4 to the 5 to the x, 10 to the x power. No? Right. You can draw them all by drawing the line that's a mirror image across the line y equals to x to all these exponential functions. 2 to the x, 3 to the x, 5 to the x, 10 to the x. Good. All right, what would this be? Negative log base 2 of x. And so just kind of work our way through a rough sketch of what this is. So first of all, if you're not really sure, I think it makes a little sense to begin by thinking about f of x equals to 2 to the x, first of all. Right? That gives you some sense of what the graph will look like. So this graph begins this way. I know it's going to have this sort of a shape. Right? And then if I think about the line that reflects across that one, I'll get to log base 2 of x. And a really ugly equation. So this one here is the inverse function, which is going to be x, which is log base 2 of x. Okay, so now the only thing is this minus here. What happens when we multiply the output of our function by a -1? It's a reflection about the x-axis, right? All previously positive numbers are now going to become negative numbers, and all previously negative numbers are going to become positive numbers. So it's a mirror image reflection about the x-axis. Good. So here I'm sure we have a nicer picture over here. Here. And so here is our log base 2 of x, right, which is a mirror image across the line of y equals to x of this function over here that goes this way. Here's 2 to the x power. Its mirror image reflection is log base 2 of x. And now if we do a reflection about the x-axis, we get this red one to be our final solution. Any questions? No? Maybe? No. What about this one? How is this one related? Well, again, we start off with 2 to the x power. Then we can get to log base 2 of x is this one. And then this one we know is a mirror image reflection about the y-axis. Right? I should have labeled it. This is our y-axis. Here is our x-axis. So it should be something over here that's a mirror image about the line, about the y-axis. Good. I'm sure there's a nice picture of it down here somewhere. Here. Good. So if we think about the line y equals to x, which goes across this way, there's y equals to x. We have this exponential function that goes this way, like this. This is 2 to the x. Its mirror image would be over here, which goes this way. And then if we reflect that about the y-axis, we get to this one, which is what we were asked about. Log base 2 of negative x. Any questions? Okay, so from the graph you can see the domain of the function h is, the domain becomes negative infinity to 0, and its range is still all real numbers. Good. Any questions? No? Okay, common logarithms. Common logarithms, or the common logarithm, is logarithm base 10. So just like with roots, square root of index 2 in the roots, index 2, this thing is so common, so popular that we just ignore it. And by default, if there's nothing written there, we assume it's a 2, right? So square root of 64, we assume that that's a 2, and that's how we know that the answer should be 8. Okay. Well, same thing here. By default, if you don't see a little index to our log, by default it should be a 10. Right? We have a base 10 number system. 10 has got a lot of nice properties to it. So by default, we like to work with 10 pretty often. So if you don't see a little index, it means base 10. And so log of 10 means that there's a little index here of 10. Right? And the reason this is a 1 here is because if we have a little base here, 10, well, I shouldn't put it in if we have a little base 10 by default in there, then this is telling you that this raised to this power must be equal to whatever's in there. So 10 to the first power is 10. And then for a little 10 there, then 10 raised to the second power is 100. That's true. Okay. And then, well, what if they're not whole number values, if they don't work out quite as nicely? So if we have a log base 50, then we really want to ask ourselves, right, when you see this, when you see log, log of 50, man, it's ugly. Log of 50, all right, so by default there must be a little 10 here. Since there's no index, that means I can just insert a little 10 in there. And when they're asking you what this means, equals question mark, right? In your head you should be thinking 10 to what power, what exponent can I raise 10 to in order to get a 50? Now it might not be a nice whole number like here, 10 to the first power was 10, 10 to the second power was 100. So it might not be a whole number value, there might be a decimal value. 10 to what decimal value equals to 50? So even if we don't really know the exact answer, we kind of have a sense of what it should be, right? It's somewhere between 1 and 2. Just like roots, right? We know that the square root of, let's go back up here. We know that the square root of 64 is 8. We know that the square root of 49 is 7, right? But what's the square root of 53? Right, like, I don't know, it's not a whole number value. It's some decimal value somewhere between 7 and 8. All I know is that it's got to be some number so that when I square it, it equals to 53. Right, that's what this is saying. The answer will be something, I don't know, A, but I know that the special property of this number is going to be that when I take A and I square it, the answer will be 57. Sorry, 53. Such that when I square whatever answer that is, I should get 53. Good. So same thing happens here. I don't know what the answer is. It's some decimal number. It's bigger than 1 because 10 to the 1 power is 10. It's smaller than 2 because 10 to the second power is 100. So it's some decimal value between 1 and 2. And of course, I don't know how to get that number exactly. I conceptually can understand what it's trying to give me. I can leave it as a representative decimal with the notation log of 50. Just like we do with, say, root, we often work with, say, root 3. I don't know what that is. I know it's some decimal so that when I square it, the answer is 3. But since I don't really know the decimal, I can just leave it like that, and this represents that decimal. So here we could just leave it like that. Log of 50 is a decimal. It's some decimal that has a certain property, the property being that 10 raised to the power of this decimal equals to 50. Right? 10 to the power of whatever this decimal is, log of 50. Whatever this decimal is, it has the property that 10 raised to that decimal is equal to 50. Right? Good. But we can use technology to get an approximation. So let's just go over to your calculator so you can see where that button is. So logs are really popular, and we have nice, easy buttons for logs. So wherever you're at, let's quit out of there, clear. And here we have a special button just for logs. And the common log is very, very popular. So we have a special button right here that just says log. And by default, whenever you see log, it's base 10, right? So let's just try some obvious ones. Log of 10, the answer should be 1, right? Yes, 10 to the power of 1 equals to 10. And log of 100, the answer should be 2, right? 10 squared is equal to 100. Good? Okay, so this guy's working. So now if we just put log of 50, it'll give us a nice decimal approximation. right? And what's special about this decimal? This is the decimal such that if we take 50 and raise it to the power, clear. If we take 10 and raise it to the power of this decimal, approximately 1.698970004, 10 to the power of this decimal should be pretty close to 50. Some rounding issues, but it gets pretty close to 50. Good. So 69.89.7 is the answer. Log base 50, 1.6989.7. Right? And that's the decimal that belongs here. We knew that this had to be bigger than 1, but still less than 2, and it agreed. It's bigger than 1, but still less than 2. Any questions? No? 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 As long as we're using a calculator, we can graph our log function, and we can use the values to sketch its graph. Right? So I think that this is probably an overkill. We've already spent a lot of time on this, so I think we could do that. Use a calculator to find the approximate values of log 10, and then use these values to sketch its graph. Okay, so I'm going to just skip on over to the answer to this thing. I don't think we can answer this if we wanted to. Okay, so we can create a table, right? Log base 10. We can use our calculator to create these values. And then, no surprise, it has the same shape as all the other ones. Base 2, base 3, base 10. It still has the same sort of shape, just different specific values depending on the table. Any questions? Any questions? No? No, 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 no? Okay, the natural logarithm. Another one that is very, very popular, very important, is to use base e. Right? Remember, we developed that number e just a few sections ago. It is the limit, right? The limit as n goes to infinity of the function 1 over n. Right? E is equal to the limit as n goes to infinity of 1 plus 1 over n raised to the nth power. Right? And what this notation meant was that we replaced the n with a 1, replaced the n with a 2, replaced the n with a 3, replaced the n with a 4, dot, 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 dot. So as we kept going and eventually plugged in very, very large numbers for n, and then raised it to the power of this very, very, very large number, we saw that this thing started to approach, right, as n goes to infinity, this thing started to approach a decimal value, 2.7182 dot 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 dot. So wherever this was approaching, this was the number e. We'll spend more time with this notation down the road. It's kind of a rough introduction at this point. There'll be more specific definitions of what this means later, but hopefully we have a good sense of what that means. Okay, so that number was special. There's a lot of great reasons for why we use that number. And so we develop a whole new notation for it. So log base e is called the natural logarithmic, and it's denoted by ln of x, right? So log base e of x is ln of x. I say we develop a new notation for it because it's special. That's not quite it, right? I mean, math is not developed in a laboratory. It's not like we sat down and thought about how to develop math. Math is, a combination of ideas from different people and different cultures all around the world, everyone kind of contributing. Sometimes they're collaborating. Sometimes they're not really collaborating. Sometimes they're competing. Sometimes they're not even alive at the same time, and they kind of pick up on each other's work. So there was some great mathematician that was doing work on this area of math. And when you're the new person developing an area of math, new ideas, you have to kind of invent your own notation for your ideas. And so sometimes one style of notation is used to express an idea. Somebody else is thinking of the same sort of ideas related. Sometimes you don't even know that they're related, and you come up with your own style of notation. And then it takes a while before people kind of realize these two things are kind of related in one way or the other. At any rate, that's one of the big hurdles in math, that we would end up having lots of different styles of notation to express similar ideas. You'll see a lot of that in calculus. There's a lot of different notation styles that we have to adopt that are all related to each other, kind of adopted by different mathematicians at different times in different cultures and different languages. And over the centuries, we've kind of slowly molded it into one little packaged up deal. But it largely depends on your author and stuff. So ln of x is a notation style developed by somebody in a particular area of math, and it involved this number here, this e value, whereas this notation of log was developed by somebody else, and well, we kind of blend them together. And so there are authors that often use ln of x, and there are authors that really like to use the log notation. So we just kind of have to be aware that they are similar to each other, right? So both of these are related to the exponential function base e. So if we have f of x equal to e to the x power, and we want to go backwards on this function, well, that would be this, log base e of x or ln of x. They both mean the same thing. Any questions now that I went off on that little rant? No? Okay, so we have e to the x power having its usual shape for any exponential function base a to the x power where a is greater than 1. Remember, you can always think about this as like 2.7183 approximately. And so its inverse function is going to be a graph that's a reflection about the line y equals to x. So this red one represents its inverse function, noted as log base e of x or ln of x. Good. And as usual, this is true only if it's true that e to the y power equals to x. Right? Remember the little circle. This is the same thing as log base e of x equals y. Right? This thing is ln of x. Same thing. And so the little circle, e raised to this power must be equal to that. And that's how we get this. Any questions? No? Okay, so all the same properties that apply to logs apply to log base e, since it's just one of those iterations, right? So we had a whole table yesterday that showed some of the properties of log base a, and all of those properties apply to log base e, and therefore they can be rewritten in the form of ln. Right, so here's a table consisting of those properties. Right? What does this mean? Remember, this is log base e. Log base e of 1 equals to 0. Log base e of 1 equals 0. That's true. E to the 0 power equals to 1. That's true. Log base e of e equals 1. Right? That's true. E to the 1 power equals to e. Right? And that's how we get this one. E to the 1 power equals to e. Yep, that's true. Whenever we have it this way, well, this is kind of an obvious thing. If we have log base e of e to whatever power this is, let's make it a happy face. E to what power equals to e to the happy face? That's what this is asking. Well, obviously, happy face. E to the happy face equals whatever is in here. So whatever is in here must be a happy face as well. Wow, that's the ugliest happy faces ever. This raised to that power must be whatever's in there. Good. So that's why this is true. E to the x power equals e to the x power. So ln of e to the x equals x, right? Another way to think about it is the ln function and the exponential function base e are inverses of each other. They undo each other, therefore it must be equal to this. Good. And we covered this one yesterday as well, where we had something like this: a raised to the power of log base a of whatever's in here. Let's make this one a sad face. Log base a of sad face, and then we take that and have a raised to the power of that must be equal to the sad face. Right? You have to kind of think about why that is. This, right, conceptually, what this means is that this represents some decimal value, so that a to the power of that decimal equals to a sad face, right? So kind of hold that in your head that this must be a decimal, right? This equals some number. Just like root 3 equals some decimal. I know what that decimal is, so rather than writing down the decimal, I can just write this notation representative of that decimal. Good? So it's a decimal that exists so that when I square it, it equals to 3. That's why if I square this whole thing, it equals 3. Right? Okay, so this is representative of some decimal. There is some decimal out there so that a to the power of that decimal equals this sad face. Now take a and raise it to that decimal. What does it equal? Well, by definition, it equals the sad face. Good? Or you can think of these two as undoing each other. And that's how we get this property here. E to the ln of x equals to x. Any questions about that? Kind of, maybe. Okay, what's this going to be? Ln of e to the x. Remember, e to what power equals to e to the 8th power? Well, it's got to be an 8, right? E raised to this power must be equal to this. And there's a little e there. So e to the 8th equals e to the 8th. Yep. So that must be an 8 there. Good, good, good. Pretty good. Okay, to answer something like this, why don't we manipulate this a little bit first to rewrite this as ln of e to the negative 2 power, and then it becomes similar to the one right before. E to what power equals to e to the negative 2? Well, it's got to be a negative 2. Good. And here, well, we can just approximate. I think it's just letting us use the ln button in our calculator to find this answer. But whatever this decimal is, some decimal number, it's got to be something so that e raised to that decimal number equals 5. Good. So we can just use our calculator, and the natural function is so popular that it also has its own button on your calculator. And these are typically the only two easy buttons on any calculator. So we had this button that has log, remember that's base 10, and then ln is also on there. So for example, ln of e, that should be a 1, right? E to what power equals to e? That's got to be a 1. Good. And ln of e to the 2nd power. Well, let's make it 3rd power. If I have e to the 3rd power, ln of e to the 3rd power, that's just got to be 3, right? Or I can turn it into a decimal. I can say, what is ln of? Okay, e to the 3rd power, that equals to that ugly thing. So now if I take ln of 20.08553692, e to what power equals this decimal? Well, it should be approximately 3. Good. Okay, so now we can find the answer at ln of 5. e to what decimal equals to a 5? I know it's got to be bigger than 1, because e to the 1 power is 2.718, right? And I know that it's got to be less than 2, because 2 to the e to the second power is 2.718 squared, and that's got to be bigger than 5. So here's our answer. 1.60943791 dot 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 dot. And if it works, then it should have the property that e raised to the power of this decimal should be pretty close to 5. 1.60943791 enter. Pretty close to 5. Good. Questions, questions, questions? What, 38, I think it was? Any questions? Questions? 9438. Okay. Right, and that's because e to the power of 1.609438, oh, that's really bad, equals to approximately 5. Approximately. Any questions? Any questions? Any questions? Okay, find the domain of this function. All right, so the domain of this function, we know that this is base e, ln base e. We know that the general shape of this graph should have a shape that kind of fits this form like this, right? ln of x should look like that. So the domain has to be all positive values, real numbers. So whatever goes in here, whatever this input is, it has to be bigger than 0, greater than 0. Good. So that's what we do. We have to set that up and solve for it. 4 minus x squared has to be strictly greater than 0. And now we solve for our values. Okay, so what we have to do is factor this. We end up with 2 minus x times 2 plus x greater than 0. And I have to figure out what values of x produce this. So I would do this by the method where we put 3 number lines all above each other. So here is 0 on the number line, here's another number line, here's another number line. So here we're going to only consider 2 minus x. Here we're going to consider 2 plus x. And here finally we're going to consider the multiplication of 2 minus x times 2 plus x. Okay, all right, so what we want to do is think about what value of x would give me a 0, and so 2 minus blank, that would be a positive 2. So if we put a positive 2 here, this would be the 0 for this value there. And then if you go bigger than that, if we put a 3, a 4, a 5, a 6, we end up getting negative values over here. Right, here's our 0. And if we put values over here like 1, -1, -2, -3, all those values, for this, we end up getting a positive answer. Right? 2 minus 1 is 1, 2 minus 0 is 2, 2 minus -1 is positive 3. So they're all positive values in this direction. Good. Okay, now looking at this, the new 0 will occur at -2. Here's -2. Here is where a 0 will occur for this one. 2 plus -2 is 0. And if I put numbers in this direction, it becomes positive. Right? 2 plus 0 is positive. 2 plus 1 is positive. 2 plus negative 1 is still 1. It's positive. So it becomes positive in this direction. Therefore, it's going to be negative in this direction. Good. Okay, so now we finally think about the multiplication of the two. So in either way, if you replace these x's by a negative 2, one of them is going to be 0, so the whole thing becomes a 0. So here's a 0. And then if we replace it with a positive 2, it becomes a 0 as well. For any input of x that's on this side, we end up with a negative times a positive, which ends up being a negative. And then over here, for any x value that is to the left of negative 2, we end up with a positive times a negative, which is also going to be a negative. And then for any value between negative 2 and 2, when we multiply them, we end up with a positive times a positive, which gives you a positive. Now we know that for these two to be a positive value, it must be true that x must be a number trapped between negative 2 and 2, not including the endpoints, because then that would actually give you 0. Okay? So in order for this to be true, this is true if x is less than positive 2 but greater than negative 2. Right, so that's our domain. Our domain is going to be this, or we can also write it as negative 2 comma positive 2. So there's different ways to get this. I like this 3-number line system thing. You know, after you do it a couple of times, you go through it quickly. So I know it takes a long time the first few times. But like anything else, once you get used to it and you kind of get a sense of it, it goes by faster. And also, once you have a more complicated situation, then this gives you a framework from which to kind of break it down into little pieces and figure out the regions when it's positive and regions where it's negative. Okay, so let me walk through this one more time. First of all, I want to know the domain of this function, right? So I know that the domain of any ln function must have an input that's greater than 0, right? That I can't put a negative number into here. So whatever you choose for x, once we square it, once we take 4 minus the square of the input, this result must be greater than 1. Because if you choose some value, like let's say you let x equal to 5, we'll end up with 4 minus 25, which gives you ln of negative 21. And as we see from the graph of ln of x, there is no such thing as ln of negative 21. Right? So let's begin with that. So if we have ln, if we let x equal to say positive 5, and let's say negative, let's say positive 5, x equals to positive 5, then we end up with 4 minus 5 squared, which then gives you ln of negative 21. And we know we have a problem, right? That's undefined. Undefined. All right, so that means that 5 is not in the domain of this function. Okay, so what is the domain? We have to figure out all the values we can plug in. So we have to make sure that whatever values we plug in result in a positive input value to the ln function. To do that, we bring that over and we solve this. What values of x will produce a positive? Next, we factor it. We see that this is a difference of squares. This is 2 squared minus x squared. And if we recall back from factoring, we had this property that if we have, well, we had it normally in the form of a squared minus b squared. If we see something squared minus something squared, then we know that this factors this way, a plus b, a minus b. Conjugate pairs like this, they're both identical except one has a plus, one has a minus. So here I noticed this was 2 squared minus x squared, so it must be 2 minus x times 2 plus x. If we FOIL this whole thing out, we see that we get back to this. Okay, so now it's tempting to say, well, let me separate this into 2 minus x is greater than 0 and 2 plus x is greater than 0. But we don't want to do that. Instead, we want to think about the combination of the two, right? We don't just want to know when is this positive separately, when is this positive. Sometimes they affect each other, right? Because we know that if this is negative and this is negative, then the output is actually positive. Okay, so we want to think of them together. To do that, one way of doing this, and like I said, you might have your own. If you have your own way of doing this from prior math teachers, that's fine. But what I do is break it down into pieces. One number line, another number line, another line. 3 number lines. All of them have 0, right? So this is x, this is x, this is x. They're number lines. All of them at 0, so that all of them lined up against each other. This first number line is only going to take into consideration 2 minus x. That's it, just this one by itself. So here, what kind of an input would give me a 0? That's what I'm thinking. And so the positive number 2, if we input a 2 into here, 2 minus 2 is 0. And then from that point on to the right, like a number 3 or a number 4, if we input any of those numbers, we're going to get a negative. Right? So 2 minus 3 is negative. 2 minus 4 is negative. 2 minus 5 is negative. So it's negative, negative, negative that way. Here's a 0. And then in this direction, we're going to get positives. If we plug in a positive 1, 2 minus 1 is positive. If we plug in a negative 1, 2 minus negative 1 is actually 3, which is positive. So they're all positive in this direction. Okay, so now next I think of a new number line that only takes this little binomial into consideration and nothing else, 2 plus x. Okay, the new 0 will occur when x is negative 2. 2 plus negative 2 is 0, right? Here is the 0 for this one. Here is the 0 for that one. Okay, so to the right of that, just think of any number over here to the right of it, and you can just jump to the easy numbers if you want. Okay, so 2 plus 2 is 4, that's positive. 2 plus 1, that's 3, that's positive. 2 plus 0, that's positive. All of these numbers are positive on this side. And then if we put in values on this side of negative 2, like negative 3, 2 plus negative 3 is negative. Or negative 5. 2 plus negative 5, that's negative 3, that's negative. Negative this way. Okay. Finally, a third number line, again lined up right here, zeros, and lined up right here, negative 2, lined up down here. Well, that's supposed to be lined up. This is where this thing follows down here and becomes a positive 2. Okay, if I think about the product of the two, I know that negative 2, if I replace each one of these with a negative 2, I'm going to get a 0. This is going to be 0. And if I replace these x's, both of them, with a positive 2, the product of the two is also going to be 0. Is that okay? 2 minus blank and 2 plus blank. If I replace both of them with a 2, then this becomes 0, and this becomes some other number, but it doesn't matter. 0 times any number is 0. Or the other way around, if I replace this one with a negative 2, becomes some number, and 2 plus negative 2, that's 0, so the product of the two is 0. Okay, so that's why these two are going to be zeros. Now if I pick any number over here to the right of 2, one of them is going to become a negative number, and the other one is going to become a positive number, and when we multiply them, a negative times a positive equals a negative. Okay. If I pick any value to the left of negative 2 on the number line, I end up with one binomial becomes positive, the other binomial becomes negative, and a positive times a negative equals a negative, so I know all of these values will be negative. And here's the sweet spot, right in the middle, between these two numbers. Anytime I pick a decimal between negative 2 and positive 2, I know that both of them are going to give me a positive number times a positive number, which means the output will be positive. Just to kind of throw a number in there, for example, 1.2. If I replace this thing with 1.2 and I replace this one with 1.2, I know this is going to be positive. 2 minus 1.2 is a positive number. Positive number. And I know that 2 plus 1.2 is also going to be a positive number. And a positive times a positive equals a positive. So I know that 1.2, I mean, I don't know what the answer is, and it doesn't matter what the answer is. I just want to know if it's positive or negative, and it's going to be positive.